when you have electrical conducting object like any particular shape like this, one thing for sure that you know that is the electric field inside is going to be equal to 0. And we said that because the electric field is inside, the tangential electric field on the surface is going to be 0. That means at any point on the surface of this conductor, the electric field is going to be always perpendicular. Perpendicular means it makes an angle of 90 degrees. It's always normal. Normal or perpendicular, both mean the same. Because there is no tangential electric field. Why is that so? Let's see if it's got to do anything with this relationship of the electric field is negative gradient V. When you say gradient V, what are we talking about? Gradient means change of something in space, right? Gradient is change. Yeah? Well, it's dV over dx, dV over dy, so on and so forth. Before seeing that, let's define what is called as an equipotential surface. Equipotential surface is that surface in space where all the points on the surface have the same potential. Equi means same. All the points have the same potential on that surface. And when you have all the points to be at the same potential on the surface, that means there is no change in potential along the surface. That means all the points can be at 2 volts. All the points can be at 5 volts. All the points can be at 10 volts or 100 volts or 1000 volts, but they are all the same. That means there is no change in potential along the surface. Which means what? This gradient of V along the surface is 0. Which is exactly the same case for a conductor, because when you take this point and this point, the potential is going to be the same. Because a perfect conductor, right? How do you short circuit from one potential to another? You will just take a piece of wire and connect it to the other wire, right? That piece of wire is a very low resistance wire. In fact, 0, you can approximate it to be 0 resistance. There is no potential drop in the wire, so that this point and this point are at the same potential. For example, if you have a certain circuit like this, you want to have some other circuit like this potential to be the same as this potential. What do? You connect a short circuit, right? You connect a short circuit, a piece of wire from here to here, then this potential and this potential are at the same point. That means there is no change in potential along the surface. That's exactly what a conductor does. What a good conductor, for example, copper does. So there is no change in potential along the surface, means the electric field along the surface is going to be 0, means there is going to be electric field only perpendicular. So it's kind of falling in place here. So what other advantage do we see? Yeah, when you have an equipotential surface, there is no work involved in moving a unit positive charge along the equipotential surface. That means, right, from here to here, when I move, there is no electric field. So if I move the charge from this point to this point, there is no work done. Because in conductors, the charges are free to move. There is no real work to be done. So if you were to imagine a unit positive charge, you guys know that the electric field is always perpendicular. I mean, radially outwards. Then you can go ahead and define those points that have the same potential. All these dotted lines which appear like spheres, these are the equipotential surfaces. That means any point here or here or here or here or here or here, all of them are going to have the same potential, which will be different from all the points in this sphere. As we go out, the 1 over R kicks in. The voltage is going to be proportional to 1 over R. It will decay, yeah? If you look at the R versus 1 over R curve, it's going to go down like this. This is 1 over R. It's going to be decaying.